Hello students, today we are studying, today's topic is equipotential surfaces, but just like other classes, we will be taking a quick recap first. That is what we have studied very quickly in before starting equipotential surfaces. We studied electric field intensity. Remember, we studied electric field intensity and also we studied potential. At what? Due to again the same old example, there is a charge and at a different points at this point, let us say R is any point, means R, then that point is let us say P1 and somewhere we took the point, this is any point, right? So what we did is we just increased the R, this R, the distance of the point from the charge is increased, and for various positions what is the electric field strength we calculated and what is the potential we calculated. What is it? 1 by 4 pi epsilon naught q by r square, and the potential was 1 by 4 pi epsilon naught q by r. Remember? So from here we concluded that electric field strength is directly proportional to 1 by r square or inversely proportional to the square of the distance of the point from the charge, and the potential is directly proportional to 1 by r. Fine. And we graphically represented that as what? See, separately when we represented graphically, this also, E also is like this only, V also is like this only. Now the question is a famous question that to show the variation of electric field intensity and the potential with the increase in the displacement of the point from the charge. So you take on the y-axis E or V. This we are taking the y-axis. So how this comes? Now see, E also is a decreasing with the R and V also is decreasing R, but in this case, this in the denominator R square is there. So E will be coming very sharply, right? Very sharply it is coming. This is E. And V also, let me take in a different color. V also will fall only, but it will fall with less steepness, right? So if I say this is V, this is, which is equal to, which is directly proportional to 1 by r square, whereas V is directly proportional to 1 by r. This is the answer to the question. By the way, this question gives a quick recap and a comparison between E and V. Now let us start with the concept of what are equipotential surfaces. Equipotential surface is nothing but a surface every point is having one potential. What is potential? We have studied already. Now that surface in which all the points are of same potential, that is between 2 points potential, there is no potential difference between 2 points on an equipotential surface. Remember? So if here also it is, let us say V, here also it's V, here also what's the potential? V. At every point on the surface, if a potential is V only, then we will call it as one equipotential surface. Now let us understand some theoretical aspects regarding that. In which direction the electric field intensity will be? Now see, the field intensity of equipotential surface, let us say it is at some angle, electric field intensity is at some angle, let us say E. Now whether this will be possible or not at any angle, so let us say it's making angle of a theta with the horizontal. In this case, E will be having two components, E cos theta and E sin theta. Now see, E cos theta is along the equipotential surface. Please understand very nicely with attention whether this scenario will be possible or not. If there is a force here, when work is done, now see, if from one point to another point, in mechanical you remember, or everywhere, if a charge, we have studied the work done of a charge also, so why go to the mechanical example again. Let us say from point A to point B, it is we are moving and the electric field is in this direction. then against the electric field a unit positive charge we are moving. Why in unit positive charge only? U plus q you can consider whatever. A charge is moving, then you have to push it because the plus charge will be pushed by E. So you have to push in the opposite direction to make it move from A to B, right? So by doing so you are doing some work. So whenever work will be there, some work will be possible only when there is a force in the same direction, in the same plane. In the same direction or opposite to it, but if there is a force, work will be done. Now in this case you see, if E cos theta there is a force in this direction, then work will be done in moving it from point to point, work will be done. Now what is the definition of equipotential surface? Work has not to be done, there is no potential difference between 2 points. And potential is what? Work done in moving it from, what is the potential? Let us say A is 1 point and B is 1 point. What is the potential difference between A and B? The work done in moving a charge from A to B is the potential difference between A and B. Now, but by the definition of equipotential surface, we already said that there is no potential difference between these two. The potential of A is VA, potential of B is VB, and VA is equal to VB is equal to same V. Then only we call it a potential surface. Now that is the reason having a force along the equipotential surface is not a possible scenario. Not a possible scenario. Now if a component along the equipotential surface is not possible only, then the only possibility is electric field intensity must be always perpendicular to an equipotential surface. Now two main aspects, theoretical aspects to understand equipotential surface clearly is: one, electric field intensity is always perpendicular to the equipotential surface. And second aspect is, which also comes in form of a question, whether two equipotential surfaces can intersect each other. Think of two equipotential surfaces. Let me take one surface like this and another surface. Let us say this is another surface. These are two surfaces. Let us say this is surface A, this is surface B. Now if there is a cross section, again we see one problem is statement is two equipotential surfaces can never intersect each other. Now see, first statement said, which is of understanding of equipotential surface, is electric field intensity is always perpendicular to the equipotential surface. Now to prove this statement, what we did, let us say it is not perpendicular. We took that scenario and showed that that scenario is not possible. Just like that, what we will do, two equipotential surfaces can never intersect each other is the statement, understanding. Then we will say, let us say two equipotential surfaces A, B are intersecting each other. We are assuming that, and again we will prove that this is not a possible scenario. Line only, see, this is one plane, this is one plane. If two planes will intersect each other, two planar surfaces will intersect each other, at the intersection one line will come, right? Let us say this is the line, and this is. Now the points on this line will be having some potential, right? And since this equipotential surface, this potential will be, let us say, V, everywhere, at every point along this line, the potential is V only, guys. Now, what is VA? Now, on A plane, whatever point we take, those all will be having same potential as VA, and this line also is on A only. So, this must be V, right? Now, similarly, now consider the VB. Potential on VB will be equal to, now this line is a line on the plane B also. So, VB also must be equal to V, because at different points on B must be having same potential as this line, because that line also is a line on that only. So if VA is equal to V only, VB is equal to V only, then VA is equal to VB. Now the potential of a plane is equal to the potential of a B plane. Potential of a surface A is equal to potential of surface B. Then how these two can be different surfaces? This is the same equipotential surface, yes or no? So this also is not a possible scenario. That's why the proof is two equipotential surfaces can never intersect each other. It's correct. Now to say this, there is another explanation also using the first statement. E is always perpendicular to the surface. Now see, if we will take the cross section N and S there, if we look at A, what will be the direction of E? The direction of E, that is electric field strength, will be perpendicular to A, plane A, perpendicular to surface A. So let us say this is perpendicular. See, in 2D, actually this is coming out of the plane A. So coming out this, I am in 2D, I am showing like this. Okay, it's coming out. It's perpendicular actually. Now to B also, to VB also, there will be at the same point. What is the direction? Okay, let me show in red if blue is not, green is not visible. This is E. Now at the same point, find the perpendicular to B. Let us say this is this way. So for two planes, two perpendiculars will come out, and two direction for the same vector E is not a possible scenario again. So that is why from that perspective also we can say that two intersection of a two equipotential surface is not a possible scenario. So opposite of that, two equipotential surfaces can never intersect each other. So this was the theoretical understanding. Now we are going to understand equipotential surface with a little more depth through mathematical derivations, etc. Now to understand the equipotential surface with the little calculations, etc., we have to find out the relationship. We have studied the potential till now. What is the relationship between, we have studied electric field also, and we have read potential also, electric potential also. What's the relationship between them? We will see in the light of equipotential surfaces. Let us say there are two equipotential surfaces, surface A and surface B. Both are equipotential surfaces, let us say. Now the gap, the distance between them is dr, let us say. This is a very small distance we are taking, but just for making you understand, I am showing this one. Dr is the distance between them. So VB is the same potential everywhere on B, and VA is the same potential on A. Now what is the gap between VB and VA? Let us say that gap in potential is dV. And dV is equal to VB minus VA or VA minus VB. It depends which is bigger. So bigger minus smaller is the gap between them. Now let us say that this is positively charged, this plate is positively charged, positively and uniformly charged. Now you guess, you tell with confidence what is the direction of electric field strength. Now what is the direction of E? These are a vector quantity. This is a vector quantity, right? Though potential is a scalar quantity. So if this is a vector quantity, it will be having some direction. What is the direction of that? Now see, from positive to negative all will go, right? From positive to negative, from positive to negative, from positive to negative, like that. Instead of showing so many lines, I am showing only one line. Oh, it's not basically red, that is only one line. This is the direction of E, from positive to negative. Fine. Now imagine if I move a unit positive charge from B to A. I am moving one unit positive charge from B to A. These two are plates like this kind of plates. From B to A, if I move, I have to move, the displacement will be dr, right? But it has to be done against E, because the positive charge will be pushed by E, right? So against that, if we are moving, if I am moving it from B to A, I have to do some work, and that work is nothing but work done from B to A when we move, that is what. And between VB and VA, which is greater? VA is greater, right? always along the electric field intensity the potential is decreasing. This you remember. So VA is greater than a VB. So what we can make, this is VA minus VB, that is the work done in moving a unit positive charge between the plates, that is through a distance dr. So what we can say, this is dV, and dV is equal to what? E dot dr. E dot dr, displacement. Now this is equal to E dr. What is the angle? E dr cos theta. What is the angle between E and dr? E is going up and dr is displacement. We are moving it from B to A. So dr is coming down. So angle between them is 180 degree, right? So cos 180 degree. And cos 180 degree is equal to minus 1, you know. So it is minus dr minus E dr. Now dV is equal to minus E dr, implies that E is equal to minus dV by dr, right? Now this is E is equal to minus dV by dr. This is the relationship between, in one equation we kept E also and V also, right? So therefore E is equal to minus dV by dr. Now for this dV by dr, one name is given, it is called potential gradient. Of course, electric potential gradient. Potential gradient, this is called dV by dr. So if we write it in words, it is said that, it can be said that electric field strength is equal to negative of electric potential gradient. Electric potential, negative of electric potential gradient. This we can state in terms of words. Hope the concept is very clear. Now to gain a little more confidence, so we will take up a few conceptual questions depending on this concept what we have just learned. Now let us take up this question where there are two equipotential surfaces given, separated by distance del L, and the potentials of the two plates A and B are given to be V and V plus del V. Here while explaining I had taken dV, here it's given del V in the question. Deduce the relationship between the electric field and the potential gradient between them. Deduce the relationship between electric field and potential gradient. It is just what we have discussed, that is E is equal to minus dV by, or del V, here we will say in the language of what is the question, del V by del L we will say, right? But the next part of the question is write important conclusions concerning the relationship between the electric field and electric potential. This also we have studied already. What are the important conclusions? That one conclusion is direction of electric field intensity. Always equipotential surfaces give the direction of electric field intensity. How? Electric field intensity, it's given, see, B's potential is greater than A's potential in this case, right? V plus del V. So it is V. The potential of A is V and potential of B is V plus del V, something more than V. So higher potential to lower potential only, always the direction of E. So in this question, E's direction is this. So from the potentials of the equipotential surfaces, so we can find out the direction of electric field intensity. This is the first point. And the second important conclusion is, second and third important conclusion we have studied already. In fact, this question we have studied in the first go. What is that? The second important conclusion is E is always perpendicular to equipotential surface. No work is done. Work done is equal to 0 for equipotential surfaces. So in one equipotential surface, if you move one charge from one point to another point, no work will be done, because potential gap is 0. Only when potential difference is there, then only it can be done. In a different words, it can be said that the component of electric field intensity along the equipotential surface is always 0, which is the same point. Now let us take this question where it says Two uniformly large parallel thin plates having densities plus sigma and minus sigma are kept in the XZ plane at a distance d apart. Sketch the equipotential surface due to electric field between the plates. Let us imagine x, y, z. Let us say this is our x direction. Okay, XZ plane it is talking. So let us take this as y, and this is our z direction. Okay, now along the XZ plane, there are two equipotential surfaces. Now the gap between the equipotential surfaces is a very less. I can take it this way. One thin plate is like this, and another thin plate is below it. Plate A and plate B. These names we are giving, it's not given in the question. Now these two are separated d distance apart, it is saying, right? So distance between them is d. Now you think that it is separated between the XZ plane. So from here to here it is d by 2, and from here to here it is d by 2. Midway you imagine one plane which is the XZ plane only. There it says, the next part of the question, if particle of mass m and a charge minus q remain stationary, in between them let us say there is a charge q of mass m. Okay, it remains stationary. Charge minus q is given. Okay, charge of minus q, it remains stationary. When it can remain stationary is the question for you. See, if it is having some mass, then there will be a force on this mg, right, downwards, which will pull it down. Earth will pull it down. So it cannot remain stationary unless something is pushing. See, this is the duster. Now this is having its mg weight. If I release it, it will just fall down, right? But if it is at a stationary, if it is not falling, that means something is pushing it up, or something is pulling it up by a thread. Also you can make it a hang so that it will not fall. So that pulling force or pushing force, that together the force which is acting in the opposite direction of its weight must balance the weight, then only it can remain stationary. Yes or no? Now tell me, the charge is given as a minus q ray. Now if minus q is hanging, it is not falling, that means something has to push it up. Between these two plates, one charge is having plus sigma, another charge density is minus sigma, is given in the question. So this must be minus sigma, right? So minus charged plate should be down. Then only it can push up. Equal charges will repel each other, like charges will repel each other. So it will be pushing up, and this is having charge density plus sigma. Then only plus will pull the minus q charge. So this is pulling and this is pushing. So totally the electrostatic force will act in this direction, which is equal to what? Force is equal to E, whatever is the electric field intensity multiplied by the charge, right? So with this much force, F is equal to EQ force is in upward direction and mg force is in downward directions. These two forces has to balance each other, then only Q will be stationary or will be in equilibrium, right? So for stationary condition, FEQ is equal to mg, implies that what is E? E is equal to mg by Q. So that in the question it is asked, calculate the electric field intensity if particle of mass m and charge minus q remains stationary between the plates. What is the magnitude and direction of electric field? So magnitude we have calculated already. What is the direction of electric field? Simple, it is always from positive to negative, so it is in the downward direction. Clear to everybody? Now let us take up this question. The first part is, can two equipotential surfaces intersect each other? Justify your answer. We are done with this. Second part, are equipotential surfaces around a point charge equidistant? If yes, how? If no, why? Listen carefully. Here is a concept. Let us say plus q charge is here, a point charge. Draw the equipotential surfaces around it. Now see, what is the potential? V is equal to 1 by 4 pi epsilon naught Q by R, or V is directly proportional to 1 by R. Now R, if will go on increasing, what will happen? V will go on decreasing, right? So if we go on away and away from Q, let me make it here. If we go away and away from Q, then V will be decreasing and decreasing. But will that decrease at the same rate or not? If at 1 volt, 1 volt, 1 volt gap, we will be checking next equipotential. So let us say one potential surface means the potential at all the points on the surface will be same only. So let us say we'll take some 10 volt, then 9 volt, then next 8 volt, 7 volt, like that 1 volt gap we are checking it. Then how the equipotential surfaces will be? Now see, there will be one equipotential surface, of course, about a concentric sphere, above that plus Q, right, R. Then some other R we took. For that R also there will be another equipotential surface. There's another equipotential surface when we'll take, that also will be a concentric sphere only. If we take another equipotential surface, that also will be a concentric sphere only. If we take another equipotential surface, that also will be a concentric sphere only. Now see, that I have drawn it already, but why like so, I have to explain. If R is increasing, now equipotential surfaces are there. But the question is whether the equipotential surfaces are equidistant from each other. If yes, how? If no, why? Now see, V is directly proportional to 1 by R. That means as R increases, this V decreases. Now see, let us say for R 1, 2, 3, 4 we will take. So V will be directly proportional to 1 by 1, 1 by 2, 1 by 3 and so on. Now so on means 1 by 4 and so on. Now see, what is the gap between these two? Isn't it a half? What is the gap between these two? Half minus 1 by 6, isn't it? What is the gap between these two? Isn't it 1 by 12? So the gap is reducing gradually, right? The gap. So V is reducing gradually. It's not a gap, it is a V. V is reducing gradually. But another thing we have already studied, that V E is equal to minus V by R, or a simple thing minus dV by dr we took. So just for the sake of concept, we are taking V by R. So V, this is the V is gradually reducing, but the rate of reduction of V as we go increase R is not same. That is the reason if we take the potentials at a gap of 1 volt each, this is not uniform. See, from here to here, what is the potential gap? Then let us say the potential gap between these two equipotential surfaces is 1 volt. Now another gap 1 volt, when we find, we have to travel much more to get another 1 volt gap. We have to travel much more distance after that to get 1 volt. So in between these two, gap is 1 volt only. In between these two equipotential surfaces, potential gap is 1 volt only. In these two, potential gap 1 volt only. From here to here, potential voltage is but gap of potential difference is 1 volt only. So the potential gap, potential difference is the same throughout, but R's are increasing constantly. Is it clear? So answer to this question is equipotential surfaces are not equidistant. Equipotential surface, where equipotential surfaces around a point charge are not equidistant. Why not equidistant? Answer what we'll write is what we have said just now. E is directly proportional to 1 by R square and V is directly proportional to 1 by R. From these two we can conclude that equipotential surfaces will be at a different they will not be equidistant from each other. Clear? Now let us take another conceptual question. Draw equipotential surfaces due to an electric dipole. Electric dipole is what? Some minus charge is there, some plus charge is there. Now around the minus also there will be equipotential surfaces, right? And as we have studied already, equipotential surfaces, the gaps will increase. Like this and so on. About the positive charge also, equipotential surfaces we can show like this. Now the thing is, we have already studied that equipotential surfaces can never intersect each other, right? But if we will show simply for a negative charge only, for an isolated charge, if we will show, this will be like this, and for another isolated charge plus, if we will show like this, and naturally they will intersect each other, which is not a possible scenario. We have studied already. So how it will be? It is not a possible scenario. The answer, how to draw answer to this question will be, it will be like this, potential surfaces. So I am erasing here to make a little space. So the equipotential surfaces will be repelled by each other. They cannot come just like that. They will intersect. That is not possible. That's why they will be repelled by each other. Here I have to clarify one point. Are the equipotential surfaces real surfaces? Do they have any existence at all? No, right? Actually, there is no equipotential surfaces somewhere. Only we define in our mind only. We define one concept that all the points, the locus of all the points having same potential, we call that a equipotential surface. Now if we define the equipotential surface that way, this we define in mind only. In actuality there is no equipotential surface. Now if we define equipotential surface, so how can we imagine that the equipotential surfaces are intersecting each other? That's one impossible imagination. That's why this also we are imagining that equipotential surfaces must be in this order, so that they will never intersect each other. So this also is one imaginary. The example is like many a times we do this kind of imagination, right? There is no actual reality, but through that imagination we derive some right calculations in exact order. Just to give one recent example, the Gaussian surface in electric flux, you remember, is there any Gaussian surface? Only we imagined one closed surface to calculate the charge inside that, and mathematically we could calculate it very nicely. Actually the Gaussian surface also was not having any existence at all. We just imagined it. It's in our brain only, it's in our mind only. In the same idea only, equipotential surface also, all the points which are having same potential, the locus of all the points are having the same potential, we will call it equipotential surface. We have defined equipotential surface and we are imagining how equipotential surfaces are there, and regarding that questions are there and we have to answer this way. But all the time in the back of our mind we have to keep in view that there are not actual surfaces which are repelling from each other, which are like this. But these are, if we imagine the equipotential surfaces, those has to be like this. They can never intersect each other. Clear? We will take up another last conceptual question where it shows, let us see, 1 meter, 2 meter, 3 meter, like this is divided, and there is a graph like this shown in the question. This graph is given in the question from 2 to 3, 1, 2, 3. So x is equal to 1, x is equal to 2, x is equal to 3. From 1 to 2, this graph is a straight line, that is v is not changing, v is constant in between this. And from 2 to 3, again it is falling to 0. That means when x is equal to 0, v is equal to 0 volt. Let us say x is in a meter and v is in a volt. Then when x is 0 meter, v is also 0 volt. X is equal to 1 meter, v is something, and x is equal to 2, v is that something only, it's not changing at all, the same value is maintained. But again when x is equal to 3, to be decreased to become 0 volt again. Now the question is, draw the corresponding graph where x is taken along x-axis and E is taken, electric field intensity is taken along y-axis. for the same point. 2. Let me read the question once. It says the electric potential as a function of a distance x is shown in the figure. Draw a graph of the electric field E as a function of x. Now see, here what we can say, a straight line, which it's not a curved line, from 0 to 1 I am saying, it's a straight line. V between 0 to 1 is a straight line. Can we say that as k times x? See, since it's a straight line, x to the power 1 will be there, this you know, but v will be directly proportional to x, so some constant to x. Let us say between 0 to 1 I am writing v01 is equal to kx, and between 1 to 2 this is 0, between 2 to 3 it is minus kx, right? It is decreasing, minus kx. Now what will be E between 1 to E01, between 0 to 1 E will be how much? See, E is equal to, we have now know that dV by dx, right? Here x is the distance is taken, dV by dr we calculated already, minus dV by dx, so this is equal to minus d by dx of v, which is kx, and d by dx is equal to 1, so it is minus dV by dx, minus is there, right? So it's from d by dx of kx is k and a minus is there, so it is minus k, isn't it? Now similarly between E1 to, so minus dV by dx you put, and since v is equal to 0, 0's differentiation is simply 0 only, right? And here implies that E2 to 3 is equal to what? Minus d by dx of minus kx, and minus kx is from this much is minus k, but another minus is there, so this becomes simply k, right? Now see, here from 0 to 1 E is equal to minus k. Minus k, k is some value, so minus of something. Okay. Between 1 to 2 E is 0. And between 2 to 3 E is equal to k. So how much is distance from here to here? That much distance in the plus k, plus direction. So this is the answer to the question. Clear to everybody? So in the next topic we'll be taking on some theoretical concepts again of conductors, electrostatics of conductors, then dielectrics, polar, non-polar and all those things. So as of now this is all about electric potential surfaces only. Hope this session remained fruitful. Thank you everybody.